Hello everyone, welcome to the third part of our series on modeling and controlling a 2-degree of freedom manipulator in MATLAB Simscape. In the previous video, we defined a trajectory for the end effector and used inverse kinematics to convert that trajectory into joint angles. Then we used forward kinematics to check if the physical model could follow the path accurately. In this video, we are going to take a step further by designing a PID controller that uses torque as the joint input, which is a more realistic setup for control in robotics. And we'll test how well the robot can track the same trajectory under dynamics conditions. This diagram shows the complete control loop we are using to drive our 2-DOF manipulator using torque control. We begin with a defined trajectory in Cartesian space, which are positions in x and y and z directions, that the end effector is supposed to follow over time. These are converted to joint angles using inverse kinematics. The computed joint angles are then compared to actual joint angles measured from the physical model, producing an error signal delta Q, which is sent to our PID controller or any other type of controller that we could have, and the controller generates a corrective torque tau PID to reduce this error. However, for real robotic systems, feedback control alone is not enough. That's where the feedforward controller comes in, which calculates the expected torque based on the robot's dynamics. At the top over here, we have the dynamic equation of a robot manipulator. The first term, mq double dot, is the mass matrix, which represents the inertia of the robot. The second term accounts for Coriolis and centrifugal forces. And the third term is the gravity torque, the torque that is required to hold the robot against gravity. And the last term is the friction or damping effects. In fact, calculating all these terms analytically is very complex because of the geometry and interdependence of parts in the robot. For example, the mass distribution and link shapes make the inertia terms very difficult to derive in our model. Actually, in our model, the only term we compute manually is the gravity torque, which already provides a significant improvement when added to the control algorithm. As we will see, this simplified forward term improves trajectory tracking remarkably. But if we want to improve accuracy even further, we can use tools like Robotics Toolbox in MATLAB to compute a more complete and precise inverse dynamics model, which includes all required terms for our feedforward controller. By combining feedforward dynamics and feedback control, we make sure both predictive accuracy and robust correction, which are both essential in real-world robotic applications. As I mentioned, the gravity torque can be calculated in our model easily from the mass and center of mass of each part that are shown in this table. To find these values, we could either go to NX or CAD models to find the mass and center of mass of each part, or we could go to our model, physical model, and we could go to the links, the parts that we have imported. In the inertia part, if we update the properties based on the mass and geometry, we will see that the mass is calculated and the center of mass is calculated based on the frame that is attached to the part. I've already calculated this, and the required torque for each of the two joints is calculated over here. It is 2.51 Newton meter for the first joint and 0.55 for the second joint. Okay, we'll go to the model. There is something that I would like to correct, as I keep receiving a warning message from MATLAB. If I open the physical model and go to the end effector, since we created this end effector by copying from link 2, the port that is assigned to the end effector is not very well known to the model. So that's the warning message we get here. Although it is defined correctly in the center of the part, I would like to get rid of it and show the original frame that is assigned to this part, which is again at the center of the part, which makes no difference. Then I press OK. Then I have to do this correction. Now you see we have a port named R that we connect to the follower of the welded joint. Now it is correct. Go back to our model, we save it, and we also save it as another file to implement our controller algorithm here. I would call it PID Okay. To insert a PID controller block, you could double click and type PID, and a PID controller block is shown here. You have to delete these two, and we need one PID controller for joint 1 and another one for joint 2. So here I rename them PID J1, PID J2. Since the output of the PID controller is torque, and that is what we are going to input into our physical model, we have to change the input of our physical model into torque. So we go to the joints, and here we previously defined motion to be provided by input, but now we would like to have torque as provided by input, and then motion has to be calculated automatically. As we do so, we see that the input port to this joint is renamed to T, which represents torque. We name it also here T1, and we do so for the second joint. Okay. Actually, to compare the measured and desired joint angles, we need a sum block, as we conventionally use in our feedback control algorithms. We need a plus and minus signs. I actually replace plus and minus. The plus side comes from the desired trajectory, and the negative sign goes to the measured angle, and the outcome is sent to the PID controller. We do the same for the second joint. As we saw in the diagram, after the PID block, we have to add the feedforward controller, which is for our case the simple gravity, which are actually two constant values, 2.51 for joint 1 and 0.55 for joint 2. So here I create a constant block I type 2.51 and I also renamed the block to TG1 for joint 1, and I create a copy for joint 2. And then I need a summation block to add these two before sending it to the physical model. I create a copy from this sum. I make sure they are both plus. And then I add these two signals and send the outcome to the physical model. I do the same for the second joint. Yes. Now it's time to set the parameters for our PID controllers. If we double click on one of the PID controllers, we see that the PID controller is described by 4 parameters, P, I, D, and N, which is the filter coefficient. For this example, we would like to keep it as 100. Just to give you an example of how the system works to check whether it works correctly, we keep the proportional value to 1, and the same for the controller for the other joint. Now we run the model to see how it performs. As you see, the controller is doing terrible because the parameters that we have set for it are not optimized. So we have two options. We could either tune the parameters manually, change these parameters, and check whether our end effector actually follows our desired trajectory or not, which is pretty tedious and time consuming. As we see here for this example, we do not see the same behavior. Another approach which is recommended is to create an optimization algorithm and a cost function to calculate the difference between the measured joint angle and the desired joint angle, and minimize the difference by changing the parameters that are defined in the controller. So in order to do so, we have to have a script performing this calculation for us. If I go to the PID controller block, I first have to rename the gains into parameters that are going to be optimized. I would rename the proportional gain to KP1, representing the proportional gain for joint 1, KI1, the integral term for joint 1, and KD1, the derivative term for joint 1. The reason that we see missing variable in the field is that we haven't defined them yet. These parameters have to be read from the MATLAB workspace, which are not there yet, and we will do so in our script. Repeat the same thing for joint 2, KP2, KI2, KD2. Also, to create the cost function, we need to have these signals Q1, Q2, and Q1M and Q2M to be sent to the workspace. That's why I use a block named toWorkspace, as you see here, to send these 4 signals to the workspace. I rename it Q1. I need the same block for Q2. and 2 more blocks for the measured joint angles. Q1M, Q2M. Yes. We save it and we go to MATLAB. I have created the scripts already. First, the cost function. The cost function actually has an input in which the PID gains are stored. And then the KP values, KI values, and KD values are assigned based on the PID gain values. And they are assigned then to the workspace for our model to read those values from the workspace. And then the simulation is run. We have to make sure the name is the same as the model that we have here, because this command runs the model. And then from the outcome of the model, we derive the Q1 and 2, Q1M and Q2M signals. And then we compare these two to create the error signals and then our cost function. Since we are going to use an optimization algorithm, some of the values that are assigned to these PID gain values might result in a wrong simulation, or the simulation may not converge. That is why I forced the optimization algorithm to skip those values by this function. Now if I go to our optimization script that I have created, it actually set up some parameters for our genetic algorithm optimization that I am going to use. You could use other optimization solvers like fmincon. For now, the genetic algorithm requires me to set boundaries, upper boundaries and lower boundaries for the PID gains. For example, the PID gain for the p-value proportional gain for joint 1 is set to be selected between 10 and 50. That comes simply from experience or just from try and error. And the same for other terms. And I have set the maximum generations per iteration to be 10 and the population size to be 5. In total, I will have 50 sets of parameters in which the optimization toolbox could find the optimal value. You could increase these values to have a better and more accurate set of gains. But for now, this is enough. If I run this script, it starts calculating the PID gains, and as you see, it performs different iterations, and each iteration it sets these values to the gains, and it calculates the cost function associated with that set of parameters. And in this figure, it shows the convergence of the fit values. I have set a large cost value to the ones that do not produce a good result, but for the rest of the cost function values, you see we are finding some small numbers already. And we wait for it until it is completed. I pause the video here and wait for the optimization process to be completed. Okay, the optimization is now stopped as it has reached its maximum generations that I have set. And here you see the PID gains that are found for each joints 1 and 2. If we run the simulation with these values, we could use the cost function script to run our model. We do not have to go to the model and change those parameters manually. The values are read from the workspace. As you saw, in the beginning it has some oscillatory behavior, especially in the z direction, but it followed the circular trajectory rather well. To check that, we go to the model, we check the output. We see that the initial part of the motion, which was a straight line, was followed in an oscillatory way, but the rest of the trajectory was followed very well. This is for x direction, and for the y direction it is also rather good, but this oscillatory behavior is something that is caused by the lack of proper modeling in our feedforward controller. However, the fact that we provided gravity torques to our control algorithm has improved our control algorithm quite a lot. To check that, we could simply set these values to 0 so that we do not provide any feedforward controller. And if we save this and go to the command window of MATLAB to do the optimization one more time, you will see the difference. Okay, the optimization is now finished. Surprisingly, you see a smaller cost function corresponding to the optimized PID gain values. However, if we run the model with these values, you may notice that the vibration in the beginning is much less, and it is correct. And if we go to the first scope to calculate x, you see a much better performance in the x direction coordinate. But if we go to the z direction, we see a significant difference between our desired trajectory and our follow trajectory, and that is caused by the fact that we have not included any feedforward controller into our simulation. And that emphasizes on how important to include feedforward controller and all possible terms. As I mentioned previously, if you want to improve the model to reduce these vibrations and also remove this difference between the desired trajectory and followed trajectory, you have to use inverse dynamics properly. And to do so, you either have to have knowledge of the dynamics of your robot, which is cumbersome and very difficult, or use tools like Robotic Toolbox of MATLAB to calculate that for you. To keep things simple, I have not included that in this tutorial. I hope you have enjoyed this series of simulations in MATLAB. If so, please give me a thumbs up and subscribe to my channel for future modeling and simulation examples. Thank you.